Welcome to the most interesting part of this conference, which is about drilling, well completion, and workover. I know that we have all been waiting for this session, so we will start shortly. I'm not going to wait for the people who are still eating outside, but they will come in, and there's no power nap allowed during the sessions, so we keep it focused. My name is Sigurður Sigurðsson, but no one outside Iceland can say my name, so I'm usually called Siggi. I'm a civil engineer. I have been working within the contracting business for many years, and I'm now a consultant. Prior to that, I was CEO of Iceland Drilling. I will allow a few questions after each speaker. We run a tight time schedule because there are 6 speakers, and this session will finish at 2:30. The first speaker is Rochelle Longwall. She is Vice President of Geothermal at Blue Spark Energy. As a geoscientist with an entrepreneurial spirit, she is committed to develop sustainable solutions for harness of Earth heat. In her work at Blue Spark Energy, she is spearheading the development of novel scale removal technology to increase the lifespan of geothermal wells. Rochelle's transformative leadership has earned her recognition through the Young Woman in Energy Award for changing the face of energy and the Early Accomplishment Award from APEGA. As an ambassador with Energy Future Lab and Wing Canada, she actively promotes education, professional development, and career advancement in the energy sector. Welcome, Rochelle.
All right. Thank you, Siggi, for the kind introduction. I want to welcome everybody. I appreciate the time that you've come to join me as we talk about extending the life cycle of geothermal wellbores, effective strategies for scale removal. So today we're going to talk about 3 different buckets when we think about how do we extend the life cycle of wellbores. Maintenance is going to be the focus today, and we'll talk about 2 traditional methods, chemical and mechanical, and then we'll talk about an innovative method known as electrohydraulic pulse. So first, let's start with chemical. Common methods for chemical are inhibitors, as I'm sure you're familiar with. So this is to prevent the buildup of scale. We also can do acid flushing, bullheading, and this is after the scale has formed. As a quick overview, there's quite a few advantages and challenges, and I just want to touch on a couple of these. So for advantages, a key thing is that it is readily available, and the inhibitor can be built into the reinjection cycle. The other thing is that it can increase the productivity. Now, one of the challenges that can be faced with chemicals is that it can be viewed as a short-term solution, and this is twofold. One would have to be in how effective it is. Typically, you will have to do more treatment intervals than some of the other methods. Additionally, when we look at the longevity of the wellbore, the well integrity is really critical, and if this is used as a short-term solution, usually you're going to keep that health of your wellbore. But when you look at it as more that long-term solution, that's where there can be challenges. Now, those challenges will depend a lot on how well do you understand your brine. So if you understand your geochemistry, that's going to be critically important. And I know there's a lot of companies out here helping you do that, so that's excellent. The other challenge you have to be careful with is that there can be corrosion with the additives of certain acids. So that's something to keep in mind, and we are also seeing a shift too in regulatory nature in applying chemicals in wellbores. So the case study that I wanted to share today is from New Zealand, and they are dealing with calcite as well as silica in their producer well. So they decided to do 10% hydrochloric acid and 5% hydrofluoric acid for treatment. They also did caustic soda, so as a pH modification. This was key for them to help to reduce corrosion and act as that neutralizer. Now, some of the results that they saw was that the hydrochloric acid worked great for their calcite, and then they needed the hydrofluoric acid for their silica. The case study talks a lot about the different feed zones and the importance of understanding those and also how you're targeting them. Are you going to be redirecting acid in different feed zones or diluting it as you try to treat them specifically? They did end up doubling their production. And they did this both through acid flushing and bullheading. So now let's jump into mechanical. Mechanical, so we've got the key ones I'll talk about today is broaching, brushing, and reaming, also known as milling. So you can see here on the top right, we have our broaching tool. So it's a mechanical tooth tool, commonly used through coiled tubing. Your brushing, you've got your bristle wires there. And then we have reaming. So this is really using your various bit sizes to create that accessibility and to remove the scale. The key thing here is, especially if you're dealing with some of those harder scales like silica, you'll go straight to reaming right away. And that's where you are gonna require to bring in that rig. So some of the advantages, high temperature is a big one. So you can get up to 600 degrees Fahrenheit, which is really helpful. And then you have that ability to revive those well bores that have been fully scaled up. So that's key for this solution. And then as I mentioned, if you are reaming, you will require a rig for that. The challenge here is just understanding what those rig times are gonna be. If those rig times, depending what you run into, are unpredictable, that can result in higher costs, of course. And there is that potential to damage the completion equipment. Now, here in our case study, this is the Pico plant in San Miguel in the Azores. And their problem is they had extensive calcite scale within their producer well. So they actually had two methods of treatment. One, they cooled the well, and then they went in and did their reaming. The second time, they said, you know what, let's keep flowing this well, keep the temperatures the same. We'll have our calcite cuttings come to the surface, come into our separator, and this way we're gonna be able to really help with our results. And that's what happened. So because they were able to ream the well while flowing, that method allowed them to ensure that there wasn't a reduction in time as far as the well being out of service. And then secondly, they weren't affecting the properties of their cement or their casing because they didn't have that thermal cycling. Now I'd like to speak about an innovative method called electrohydraulic pulse. And this removes the wellbore impediments in the near wellbore region. So the electrohydraulic pulse technology, it's using a small amount of energy at surface and it's converting it into high amount of energy downhole. And this high amount of energy is your electrohydraulic pulses. So you can see here on the tool, you're actually gonna come to the well site, they're gonna unplug your coffee machine, but they're gonna make sure you have your morning coffee first, so not to worry. Plug in the tool, which will be deployed through wireline, and they're gonna send 1,000 joules down here. So that 1,000 joules, small amount of energy is gonna go through the charge unit, where it's gonna build up to 30,000 volts. It'll head through the safety device, energy storage, and then rapidly, it's gonna be moving through your power amplifier and into your electrode. And in your electrode, you have the anode and the cathode. And that electricity is gonna jump between the two. So think of the spark plug in your car. And that spark is actually gonna create an intense amount of heat for a split second, create a gas bubble that's gonna cause the propagation of waves. This is your shock waves, your electrohydraulic pulse. That shock wave is gonna move outwards, propagating outwards, which is your compressional force. Once it hits your casing or your slotted liner, it's gonna reflect off that steel, reflect inwards, and that's going to be your tensile force. This is a push and pull motion. Now, this is going to peel that scale off the edges of the weld bore. And why? Well, it actually comes all the way back to that brittle material that we're able to treat. When we have that brittle material like scale, it has a high compressional strength but a low tensile strength. So as we peel it back, that's where we're very effective at taking the scale off the edges of the weld bore through your slotted liners, cleaning that out. A few things to note here. One of the ways you can think about it, when that spark is created, that's the lightning. That's all the energy is stored in there. But then it's the thunder. The thunder is what's propagating. That's your electrohydraulic pulse, your shock waves. And that's what's going to create that ability to remove your scale. So the pulse can be completed 12,000 times per run within your weld bore. So this will treat approximately 120 meters, depending on your scale type, at about 8 minutes per meter to treat. And you can see in the top right, this is an example where you had iron carbonate scale deposit and even chiseling away. I'm not sure if you can see right here, taking a chisel, trying to get that off. It is hard to do. But with the Blue Spark tool that's been using the electrohydraulic pulsing, they're able to create a really clean weld bore. And this is key, especially when you consider mechanical, like trying to clean, especially within those divots from corrosion, very challenging. But that's important because you're not leaving behind a nucleation point for that scale to form that much quicker. And then there's also the slotted liner example there. So let's look at the advantages and challenges. So it is an eco-friendly solution. It's safe. You have a small footprint bringing in your wire line. And then the other key things is what I mentioned about just the way you're able to clean that weld bore is very different than chemical or mechanical solutions. And it has the ability to remove hard scale. So 39 types of scale have successfully been treated to date. And it is a targeted approach. Now, one of the challenges that is faced is that there is the temperature limit of 130 degrees Celsius. So if you are looking at your producer wells, this is where it's critical. Time it with when you have your workover, and similar to your other wireline deployment, it can be deployed at that time. You also require a non-compressible fluid in order for those electrohydraulic pulses to propagate. So you wouldn't be focusing on your steam phase, but rather your liquid phase within your weld bores. So the case study for the electrohydraulic pulse is from Lakeview, Oregon. And a bit of the backstory for them is that they drilled a district energy system for their small community of 3,000 residents, and they didn't touch it. And it was 14 years they had not touched it. And I think this is something we all have to keep in mind is, do we have a maintenance program? What is our strategy? Because, you know, one thing for this case is that that phone call came in, and really the reason being is that winter was about to start, and while they needed 130 gallons per minute flow rate to meet the needs of the local municipal buildings and schools, they found themselves at 88 gallons per minute. So what did they do? They actually had to shut off the well. They started using propane in the local buildings, but one of the schools in particular, the preschool, they had to shut it down completely because they had no alternative energy source. So what does that happen? What does that do for all the families there is that, you know, unfortunately, you're keeping your kids at home for preschool now. So that happened for 6 months. And the town was considering, do we do chemical? But they were very hesitant with wellbore integrity. Mechanical, the challenge there was just that there were no rigs nearby, and getting someone to bring one was very costly. So they did the electrohydraulic pulsing technology to treat goethite scale. And within 8 hours, they were able to bring that production rate restored beyond what they were hoping to 206 gallons per minute, so just over doubling it. So here is just a comparison of different maintenance methods. For the frequency of treatments, This is going to vary significantly based off your wells. But what's important to keep in mind is just that if you're doing chemical, it's something that you're going to have to do more frequently, mechanical, little less frequently, and then the electrohydraulic even less frequently. And it just really comes down to how well you're able to clean out that wellbore. And then here's some other parameters, just if it's rigless, do you have immediate results? What is the risk on your completions equipment, your reservoir, and then what are the health and safety issues? So overall, when we talk about maintenance programs to extend the life cycle of wells, this is where your fluid chemistry, your reservoir conditions, drilling regulations, economics are all going to play a really important factor. One strategic consideration to optimize efficiencies can be through combining treatments as well. So perhaps your wellbore is completely scaled up. You can come in, ream it until you're able to fit the electrohydraulic pulse tool in. And then for the remainder of the cleaning, you could pulse. Another option would be for combining chemical and electrohydraulic treatment. So you could focus on just using your inhibitors. And then where you're going to do your acidization, you could bring in your electrohydraulic pulse instead. Now, if you really wanted to, you could actually have your inhibitors, bring in your electrohydraulic pulse, and once you've done that, then you could do your acidization, and that would be extremely effective as well. So there's lots of ways to be creative in this space to optimize your efficiency, but ultimately, as long as each of you leave here with a strategic wellbore maintenance plan, then I'm going to be one happy gal. So thank you, and happy to answer questions.
Thank you, Rosel. We allow for two quick questions. Nas is going to help us. He has a microphone. Any questions from the audience?
Yes.
One question here. And also one up there. Okay.
Yeah, one question I have. Did you evaluate the risk of the integrity of the cement behind the casings for the jobs?
Yeah, good question. So, wellbore integrity. This is so important, and I'm really glad that you did bring it up. So one thing to note is that when that electrohydraulic pulse is propagating outwards, you've got between 88 to 94% of that energy is going to be reflected off your steel. Only 1.5% is going to get into your cement, but that energy that's propagating, remember, that's our thunder. So that's our 1,000 joules, right? That's not our 30,000 volts. So we're unable to affect that cement behind the casing. And we've done a lot of tests with over 1,000 operations to date and using cement bond logs to make sure that that is in fact the case. But one thing that's valuable is seeing it for your own two eyes. So I know some of you this week have come to see the demo outside the building. And Blue Spark is actually doing a demo where they are pulsing. And what's great about that is you can see the casing, you can see the cement outside the casing, and you can see that it has not been affected. So this method does maintain wellbore integrity.
We have one question over here.
So the Salton Sea well-filled scales are very hard, a lot of iron silicates and things like that. And, you know, we mostly do mechanical cleanouts, but they don't last, and we never get that skin of scale off, so that's a nexus for more scale precipitation. So do you think, I mean, goethite is pretty soft stuff. A, could you clean out those hard silicate scales with the electrohydraulic pulse? And B, where's that scale going? Because if it goes down to the bottom of the well where your production zone is, that's not good.
Yeah, thank you for that. So with those 39 types of scale that have been treated to date, we have done iron sulfides, we've done barite, we've done silica. So good news for you. For us, one of the things that's important to understand that I didn't mention is that we treat 1 foot intervals at a time. And so you pulse every 5 seconds. And yes, depending on if it's an iron sulfide or if it's a goethite, calcite, We're going to treat optimally to reach that. Now, each pulse we do is really critical because as we pulse, we're turning it towards a powdered form, which then, even though we don't do it ourselves, the operator gets that decision. But typically what happens is then you just flow the well.
Okay, thank you. Thank you, Rochelle.
Thank you.
Next speaker is Bruce Gatherer from Iceland Drilling. He's going to talk about cost of drilling. Bruce has been working with Iceland Drilling for a little over 8 years in various roles, from operation, support management role, to site project management, having participated directly in projects in Europe, Caribbean, Iceland, of course. Prior to ITC, Bruce worked for several drilling and service companies and has extensive experience in underground mining exploration drilling, civil engineering projects, such as underground metro freeze-hole drilling construction in Amsterdam, horizontal river crossing drilling, oil and gas, and of course geothermal in Europe. Over 3 decades, Bruce.
Yeah.
Yes, a lot of experience. Welcome.
Thank you, Siggy. Thank you, Siggy. What a wonderful introduction. It's quite scary to think I've been in this industry for over 3 decades now, but every day is a different challenge, and I'm still enjoying it today, and hopefully will continue doing for many more decades. I have to confess to not having any charts, statistics, or bullet points. Just a few visuals to distract you all and hopefully entertain you while I discuss a little bit about the cost of drilling. Iceland Drilling is a well construction company that have been producing high-temperature geothermal wells for over 6 decades now, mainly in volcanic regions around the world, such as Iceland, the Caribbean, East Africa, the Philippines, New Zealand, the Azores, and Europe as well. And a good few years back, we were even drilling in Germany, Denmark, and Switzerland geothermal wells as well. So a lot of what I want to talk about today is more based on our recent experiences. The high cost of drilling wells has been a long-standing topic of discussion, not only in recent times, but for many years within the oil and gas industry. And sometimes it's hard to understand why today it's labeled as too expensive, when prices have not really increased over the last 5 or 10 years. I even heard some people tell me yesterday 15 or 20 years. As many drilling companies in recent years have been struggling to break even, and we all know what happens to companies that don't make a profit, even a small one, and that's not good for the industry. The possible decline of drilling companies through low pricing will not benefit the industry, as the future drilling costs and competition reduces. Even more may start moving back again to oil and gas industry as the rig rates there start to increase, as the activities increase as well. So the more relevant question might be, how can we enhance the efficiency of drilling geothermal wells to ultimately reduce the cost, and where can these efficiencies be found? So a couple of examples. But first, let's consider the universal truth. Cheap is rarely the best solution. I've never met anyone walking into a car showroom asking for the cheapest car in the foyer. We all know what happens when we buy something that low quality, low cost. It's going to fail. Without a well-constructed producing well, it doesn't matter what type of power station is installed or how much money is invested in site investigation and well engineering up front. We could potentially look at reducing drilling costs by 30 to 50% if needed, but we need to cut out certain issues like the quality management systems, safety, environmental management, experienced crews, training, maintained and certified equipment. All these elements are costly and, of course, necessary. Yet in some cases, price seems to be the primary concern. And if projects fail or the reservoir is dry, the drilling contractor is often blamed, if not by the operator, then by stakeholders. And I feel this is unfair, since we are similar to, say, an airline company. We bring you to your destination, but if the destination doesn't have what you're looking for, you don't blame the airline company. Some might argue that the airline company covers all the cost after you purchase the ticket to bring you there. But then I would reply, when you buy your ticket, you don't ask them what kind of aircraft you're going to be flying in, the route that's going to be flown, the crew and the experience on the airline company, or the meals that are going to be served. There's a high level of control imposed and often seen in drilling contracts, which is suffocating and important to consider when looking at drilling projects. Who is responsible, and do you trust them to perform, and what is the objectives? We, of course, see tenders demanding experienced crews and high quality health, environmental safety management systems, inspected and certified and well-maintained equipment, which is good, but this all has a price. Some of the drilling equipment that we would take for a location, for example, would include a drilling rig with a mast, top drive, drill pipe, drill collars, stabilizers, MWD steering motors, casing, cement, fluid pumps, BOPs, mud tanks, recycling systems, generators, hydraulic power units, forklifts, cranes, trucks, ships, cars, the list goes on. And during transportation of a rig location, it could take up to, and sometimes beyond, 120 truckloads to move all the equipment. And the value of some of this equipment can run into easily more than $30 million, which needs continual maintenance to keep it running. But buying the equipment, of course, is the easy part. You pay the money, you wait 12 to 24 months, and you have the equipment. But you don't have a drilling rig because you also need the crew. A lot of people are also discussing transitioning of oil and gas equipment to geothermal. While being a fantastic idea based on the knowledge and experience of many within the hydrocarbon exploration industry, we need to be careful as well. The petroleum industry has invested heavily in drilling technology improvements for decades. Billions of dollars and countless hours in R&D have been devoted to finding the holy grail of improving drilling speeds, ROPs, rate of penetration, as well as improving time savings on tripping pipe, for example, where every minute counts. Service companies have also invested significantly into R&D, providing faster, more cost-effective and safer drilling solutions. But we need to understand that much of the technology transitioning to geothermal from oil and gas was aimed to save minutes and hours on an offshore rig, which have high day rates, often running at several hundreds of thousands of dollars to $500,000 a day. So the savings run into serious money when you're looking at minutes and hours. This is more than 10 times the cost of a land rig, for example. So the savings seen offshore for an hour a day may result in significant savings, but it may only be a few $100s a day on a land rig. Whereas the cost of the high-spec equipment or rig may cost several $1,000s a day in rental. So we need to be aware of the cost of some of this technology and the real potential benefit, as well as looking at the risk in case of damage, for example, or lost in hull, as some of this equipment could cost more than $1 million just to replace. That said, it doesn't mean we should not try new equipment and ideas. We just have to be careful and look at all the risks and rewards that are present. Crews, as I mentioned, human resource, or rather lack of, subject that comes up in all industries today. At Iceland Drilling, we believe our crews and support teams are vital to the project's success. An inexperienced crew with new equipment will never perform as well as an experienced crew with older equipment. Hence, experienced team with good equipment is invaluable. If we consider the human resources involved within a drilling operation, we're looking at tool pushers, mechanics, electricians, drillers, assistant drillers, derrickmen, floor hands, and roustabouts. And these teams working 12-hour shifts, 7 days a week, 365 days a year. We also have in the office or supporting crews, rig managers, safety supervisors, maintenance supervisors, QHSE, quality health and safety supervisors, procurement, administration, finance, logistics, and contract managers. So there's quite a team there. Service companies providing support to the operations include mud engineers, geologists, MWD and directional drillers. Crane operators are also needed for rig operations, as well as truck drivers and rig mast assembly teams. So altogether, around 100 people are directly and indirectly involved in a single drilling operation. Then we have the investment and the investors. Project development companies very often get the cash from investment companies or banks. And these investors are seeking, of course, a return on investment and looking to safeguard the risk to their investments, which is understandable. So what we see today in many of the project development companies turning to well construction engineering companies to create drilling programs and equipment lists to minimize the risks, which are then in turn turned into tenders and presented to well construction companies like ourselves. Now, while some of these companies have been performing in the geothermal field for several years, we also see more companies coming in with fantastic extensive oil and gas experience. However, not all technologies and methods transfer directly. So we need to select carefully the right advice from the company for the area, the project, because every location will have its own special needs, whether it be formation or geographical location. Very often we see the de-risking from the operator's side can restrict and block drilling contractors from fully utilizing their expertise within the drilling operation. Another way that we look at enhancing would be the continuity of projects. Retaining a crew that gains experience and improves with each well is crucial for the skill levels within the drilling operation. And the oil industry realized this many years ago with longer-term contracts, allowing for investments in human resources, training, maintenance, purchasing of new equipment, for example. And all of this resulting in faster, safer performance, and thus resulting in savings in the overall well construction. So it's worth asking if the operators and investors can consider flexible project timelines to enable multiple projects to form a continuous drilling operation for contractors and thus avoid start time pressures or even rejecting of tenders due to prior commitments. So we all need to try and find a balance between what's possible and what's realistic. In closing, I just want to say, when selecting a well construction company or a drilling company, think about offering more upfront involvement. And above all, select a company with a team you can trust and work together with to the successful completion for all parties involved. As the saying goes, united we stand and divided we fall. Thank you.
Thank you. Thank you, Bruce. Lars, have you seen any upright hands? There's a hand up there. So the conclusion is, Bruce, it's not expensive.
It's not, no, it's very cheap.
Okay, sorry.
Do you think it's expensive today?
The value for money.
It's value for money, yeah.
So yeah, Palomar from Reykjavik Energy. Thanks for a lovely talk, Bruce. In your opinion, what can energy companies, and let's say energy companies here in Iceland, do to improve this scenario or environment that you're in?
Thank you. Thank you for the question. Firstly, Iceland is slightly different to a lot of the global operations that we see, in that Iceland almost has a continual drilling program. So there's always activities happening in the geothermal drilling within Iceland. But what would be helpful is, again, as I mentioned, flexibility as to starting times. It goes for all areas we go to. A lot of the drilling control, the project development companies have a hard and fast date that they want to start drilling on. And then they want to, if we come in too late, they're looking to employ penalties for coming in too late. Our shareholders don't like being fined for coming in too late, so they would rather say no than take that risk. So a lot of companies, I think if there's more flexibility as to starting times so that we can fit in operations to continue on from operations that we're currently involved in, would be very helpful. So for Iceland, it's more or less the same as everywhere else, but as I said, Iceland does have a fairly continual drilling program most of the time.
More questions? One question here.
You mentioned the challenge and risk transitioning from oil and gas to geothermal for drilling. You gave the example of offshore deep water that are very significantly different from geothermal operations. But given the similarities of shale gas with geothermal, it's onshore, the return of investment on shale gas is lower than conventional oil and gas. don't you think shale gas drilling practices, know-how, technologies could be applied to drilling geothermal?
What I was saying is that we cannot use any technology coming out of the oil and gas industry. There is a lot of very good technology on the market that has been developed over the last decades. It's just that we have to think very carefully before just taking it on. We have to look at all the risks involved as well. So yes, there will be applications from the offshore and from the shale gas industry that are very relative and will help us in the geothermal industry. It's just that we shouldn't just assume everything that comes from the offshore oil and gas or the oil and gas industry in general is going to help us.
Thank you, Bruce. Thank you very much.
Thank you.
Thank you all. Our next speaker is Professor Dr. Ingo Sass. He plays two roles in his working life. He is professor for geothermal science and technology at Technical University of Darmstadt, and he is also head of the section for geoenergy at German Research Center for Geosciences in Potsdam.
Thank you. Yeah. Good afternoon, ladies and gentlemen. Bruce, you gathered your 30 years of experience. Give me your sheet to sign it. So I strongly support your vision and your sight. And my story is probably a little bit about this, and it's a mixture of many things. I have to head up a little bit. We are shortly behind schedule. So just let me introduce my co-author. So Said Kamrani is a drilling engineer at the GFZ, and we were involved in this drill. And those persons are here with Deutsche Erdwärme, German Geoenergy, and it's their project, and they drilled the site in Graben-Neudorf GNTH1. Humboldt Sebastian, by the way, is one of my master students and PhD candidates. Started here as the first year of the rest absolvents in Akureyri, since I was there a part-time professor. And so we have a strong relationship to Iceland, and we are frequently here, and that is how it is. My story is about the Upper Rhine Graben. It's very promising, many geothermal projects and so on. I keep it short, so I go over it. Let's go into this. So here you see work from Béatrice Ledésert from Cergy. You see here a principal profile, temperature profile of the Upper Rhine Rift Valley, and here is the drill site of Graben-Neudorf I will report on. And my role was the role of integrity assessment in this, and so I was in the whole process involved. And so some points I want to issue here. So this is the location of the drill site. Here is Karlsruhe, KIT is located there. There Frankfurt Airport, here Strasbourg, and there Basel. And so we are here is a crust thinning from that place to that place of 40 kilometers. And so we have here a basin fill of 3 kilometer thickness. That means in terms of drilling applications, we have to use a lot of casings, and it's very complicated to implement a cheap exploration well, to learn for a production well. So however we end, if we drill 3, 4, 5 kilometers deep in this environment, we have a multiple casing, multiple liner approach, multiple cementations. So our ability to drill cheap and dirty, to know the underground, is very limited. So it is very attractive for investors with short money to say, okay, we make a well which is serving for everything: exploration, production, injection, whatever. And sometimes you come into some problems. Then there's another Central European problem, probably not so on the focus in Iceland. We have a strong conflict of use between groundwater resources protection and climate protection using geothermal. With geothermal energy, we have to pass the hydrogeological resources. And here we see, this is a sketch. We had to drill 7 groundwater monitoring wells down to several hundred meters just to prove the evidence that our deep drill is not affecting the groundwater resources. So I don't want to take this as an example. If we come to such things in Central Europe, I think this will be the end of geothermal. So we really honestly have to come into an honest and fact-based discussion on how do we mitigate climate protection and water resources protection. We have to do both. And in Central Europe, and it's not only Germany, we are observing that the environmental administration is in many cases not even talking to the economic administration. And this gives conflicts and this costs millions of euros in a project. Well integrity, okay, it was mentioned here and you are experts, so I also get to save my time. I can just over it. Here I will citate more or less the BVIG standard. This is a norm in Germany. It's from the German Association of Oil, Gas and Geothermal Industry. And they have a standard how to assess integrity. Completion design consideration at our drill was life cycle expectation 30 years. So this is a 20 million euro question between an exploration drill and a permanent well. And then production rate about 100 kilogram per second steam, 220 DGC at 4.4 kilometer TVD. And we have injector and producer well capabilities, casing criteria to meet the standard. And corrosion was considered as a risk, but you know, we had a Mesozoic intercalation from Muschelkalk and Buntsandstein and Upper Kuiper and tertiary formations. So what do we know about hydrochemistry? There will be a hydrochemistry, and it will be inorganic. But what then? Yeah. So this was an unknown risk and prevention of casing where due to drilling phase was considered. So tieback operation were recommended. Yeah, tieback now, twofold action. Again, it was an early decision. It was a good decision to go on in one section onto a 5-inch casing instead of going away from conventional things. And it's done by L80 material because a hydrochemical threat was expected to be serious. And so this helped us to later on keep the capability to drill a sidetrack out of the 8.5 section. So this is the base case, the design case of this. And from a geological and a geomechanical standpoint of view, and from a drilling standpoint of view, we cannot save those casing intersections here because the geology is as it is. Not to talk into mind. So you have to always, can you drill an exploration well, a cheap exploration well for, I don't know, 5 million euros in such a geological environment? I would say no. And if we are trying to force the drilling operator to do it for 5 million euros, we will probably not reach the target or destination, you said, Bruce, huh? Yeah. Okay, so at the end, you see here, at the end, a 5-inch production liner was planned at about 4 kilometers depth. So perf and wash here is, we did perf and wash runs. I do not want to go over this because in the exhibition you have very competent, also with ice and drilling, very competent consultancy. And also these are clips out of a video where this is explained. The perf and wash job is very important to keep your cementation line clean and free of it, because one point of having drilling industry experience eventually not unmodified in geothermal is considering cementation and temperature. I don't know, Susan mentioned in the breakout session in Newbury there were no observations of cement setting in above 350 degrees C, I guess. Huh? Aha, okay. So there is a hydrochemical attack on the cement settlement, and we have a temperature impact. And those systems are very complicated to model, and you cannot predict them. And so you have to desperately keep your cementation room free of anything, of debris, cuttings, formation, and of ions. And ions you don't know, because the electronegativity is shifted due to an intercalated hydrogeological movement is impacting your cement settling and the performance of your cementation. So it's a critical way to go into the cementations, and so we had very professional routine cementations, but then became deeper and hotter, or let's say warmer, and however cementation failed, and so we came up with in the 958 section we had a very poor bond, and at the end, the 7-liner section also could not provide acceptable quality. And so we decided to do the rehabilitation. What you see here is just a small sketch from 2,150 to 2,300 meters. So it's not at reservoir temperature. And you see here typical chevron patterns, typical channeling patterns, and a little bit a rest of somewhat of cement and so on. But the cement job had no irregularities. From the track of record, we do not have any, I would say, unforeseen surprises in that. And so it is just, we suppose, a strong hint to the, let's say, problems in the cementation is the hydrochemical load in the system overall. So before going into this 8.5-inch sidetrack, again, the 958 and the 7-liner were not cemented adequately, so we decided for a sidetrack. Also, geological conditions applied. I will come to this later in a minute. And at the end, we could rehabilitate the most of the tracks we needed, but after perf and wash job and so on, and after cementation, we kept some sections open in the 7-inch liner. So from a well integrity standpoint of view, okay, we have a lot intercalation of a lot of layers coming to the top, but however, we have circulation over the reservoir in a section above the reservoir. I had to accept it, or I had to close down the operation. And so I cannot report on all things which were taking place here. One liner packer set, for example, opened unexpectedly. We do not know why and what happens there. At the end, we couldn't cement the 7-inch liner, and we decided for a segmented cementing in sections. Also, there were also some perforation jobs in between, and therefore, at the end, we could cement properly 2.7800 meters to 3,000 something, and this we evaluated this very successfully, but at the end. Below 3,252 meters, and somewhat we kept a line open. And from a well integrity standpoint of view, due to the multifold cementations above, I think I was supporting that it was acceptable to continue with the exploration well. Okay, then the 1.8 section was drilled into the Bunter sandstone, Mesozoic, lowest Mesozoic, at 4 kilometers depth. And the production tests were not convincing, so hydraulic stimulation could be an issue. So now the $1 million question is how to stimulate such a system through such a well to get the data. I would say no. So drill a new well to get the stimulation or close the exploration. But now our open section became to a fortune. It turned into a fortune because we had a high loss zone in the Muschelkalk section, and now we tried to explore the Muschelkalk section, and this been after some acidizing very successful. So, but you know, after the tunnel's end, you will discover the light, and sometimes we need to be the disadvantage of having a multi-layer reservoir system sometimes turns into an advantage. Similar story happened in Potsdam. So there also was a more shallow reservoir utilized than desired in the first drill. So you see here the lowest, very complex geology. The situation we are facing here, I'm talking about the Muschelkalk and Bunter section, and then there is somehow a fault, and then it goes into the Permian red beds. So what are the interpretations we have? One important point, I'm short before ending. One important point is this is the most feasible interpretation. We have a lot of surprises, but what we have and what we don't understand, and where research will be back to this project, we have Bunter hydrochemistry in the Muschelkalk reservoir. And I only can explain this through somehow hydraulic bindings over the fracture system. And since we do not have any cause or any more detailed information on the formation, we still do not know, do we hit the main fault system, the fault zone, or not. However, acidizing was successful, and summary, at the summary at all, just get out the cementation. I'm not talking about the combination of other disciplines, geoscience, drilling engineering, hydraulics, process engineering, and so on. Just the cementation part is extremely important. It is also important and eventually tricky in not being in hot superheated systems. Cement properties, of course, has to be tested for the expected temperatures. Proper hole cleaning is important, and I argued why. Centralizers, very important, and without centralizers, we will not have monitoring lines in this with fiber optics. And spacer fluid has to ensure that the cement cannot get contaminated with mud. So now my time is gone. Thank you. I'm happy to get your questions.
Thank you. Fine.
For me? I don't know.
I don't know. The water is not poisoned, I think.
I don't mind.
Any questions? Questions from the audience? One down here.
I was wondering if you can share the final result. Was the well stimulated? What's next with this well?
Okay. Yeah, I was a little bit short. Yeah. We have now about 40 cubic meters an hour productivity in the Muschelkalk, and we have a track of different acid jobs with increasing the permeability. So a measure of stimulation could be acidizing and hydraulic circulation. But however, so this statement is regarded as functionable, and now the Deutsche Erdwärme is on the design of a new production job. I don't think that we will go into the Bunter Sandstein, but still the challenging question for me also as a scientist is, why do we have in a Muschelkalk environment, which is carbonatic, a silicate hydrochemistry? This is, and so there should be a shortcut. Also the temperatures are not in accordance to the depths of the Muschelkalk reservoir. So we have a very strong hydraulic shortcut to the fracture zone. And we eventually will end up in the Permian or in the Bunter. Yeah. So this is an extreme detail and a very small volume of reservoir.
Thank you. Other questions? Bruce?
Thank you for the interesting presentation. You mentioned at the beginning that you had several investigation wells drilled alongside the main wellbore. What sort of distance away from the main wellbore were you, and did you see any contamination while drilling?
So yeah, also good question. I could give a very long answer on this.
Give us the short version.
First, if you have this is a mineral water protection area. So 40% of the total mineral water production of Germany are coming out of this field, by the way. The drilling of monitoring wells itself, it's a risk for the water resource. So sometimes it could be a good decision to do less. So I would not recommend to do so, because I was in charge for this, also for the integrity assessment, and 2 of those wells had to be re-drilled. So the distance, your question was distance. The distance is between 20 meters from the BOP to some low 100-meter distances. And they're in a kind of an logarithmic snail around the central well. And you know, and you have an online delivering of data and so on, and the authorities see the hydrochemical and hydraulic data. You know, if anything happens, you do not have the time to think and react with your deep drilling on such things. So we really have to suggest that, let's say, a better way of mitigation those problems is coming into it. So my personal recommendation would be almost make a design for the passage of the water resources and equip them in any case with fiber optics to have an in situ control on the drill and not an indirect one. That will save numbers of monitoring wells.
Thank you so much. Thank you, Dr. Ingo.
Thank you.
Our next speaker could maybe solve some of the cementing issues you had during this well that you mentioned. Dickie Alamsia, he is called Kiki, he is next up. He has been working as a drilling engineer, mostly operating in Indonesia. He has been in the geothermal industry for 7 years and is currently working for an Indonesian consultant firm called Rixis. He's about to present some lessons learned from his recent drilling campaign. Welcome.
Well, thank you. Just a small part of this team. This is actually a paper published by us, the consultant, and the project owner, GeoDipa. This is going to be discussing more about tieback cementing technique and the lessons learned from our recent projects in Dieng and Patoha, Indonesia, West Java and Central Java. The project just ended like early this year, Jan or February. So, the first line, you can see there that it differs a little bit, the construction of wells between geothermal and oil and gas, because we do not really have what's so-called a tubing. The geothermal fluid comes into contact directly to the production casing. And so we need to have good casing integrity, and we have to prevent gas leak into the surface. That's the purpose of cementing. And but the main challenge will be fluid entrapped inside casing to casing annulus. So it's here, the space here. Well, if you have a water trapped in between those casing areas and the casing got heated up, then it's going to be a problem with the casing. I mean, it could potentially lead to casing collapse. And the fracture zones, because it's a little bit different with the oil and gas, because we are actually aiming for an area with fracture. I mean, the reservoir is fully occupied by fracture zones, so we should expect for loss of circulation. I mean, the cement can go down into the reservoir if we step into the reservoir. So that could be the challenge. And to overcome those challenges, actually there are like, at least we listed down here like 5 practices of cementation techniques. And tieback is just one of those. And this tieback is actually now being in a common practice in Indonesia. I mean, if you even had a chance to visit some information about Indonesian well construction from the 90s or early 2000s, they normally use this long string methods or DSC technique. Well, they're kind of doing experimentation on how well the cement can be for geothermal wells. But the recent technique we use is tieback. The difference between this tieback and DSCs are actually DAC, you run the casing once at one time and do the cementation like in two phases from down the hole to somewhere mid, and the second phase will be from that midpoint to the surface. But with tieback cementing, you run the liner and you cement the liner, and then you run the casing on top of the liner and you cement the liner. So it's a double process of running the casings or liner and the cementation. This is just a little bit into the detail about the what happened. We're going to be focusing on answering this. What is this shear pin, bump plug, and also YouTube effect? We have here a wiper plug. It is attached to the drill string through an inserted or some inserted pins. So we insert like 6 or 8 pins with resistance capacity. I think it's around 175 psi. So it's around, in total, it's around 1 KSI or up to 1.4 KSI, the resistance. And once it is pumped, we here in this schematic we have dart plug and also this wiper plug pumped down and sitting on this float collar. Well, when this dart plug just hit this wiper plug at the top of this or at the bottom of this drill pipe, and you get those resistance, you record it, and that resistance should be called as shear pin pressure. And when it all pumped down, and when the wiper plug is just sit on this float collar, and you have a surge of pressure, like around 5 psi. We normally keep it at 1 KSI. And that pressure should be called bump plug pressure. And when everything's done, we can call it as the cement is in place. Then we release the drill pipe. So this cement slurry, and we have this displacement fluid inside this drill pipe. And when we pull out the drill pipe out of the liner, and you got some U-tube effect. Because here is different density of fluid. We normally use 16.2 ppg, and we have what is inside here, the displacement fluid with density of around, I think it's only around 12 ppg somewhere. So you have a sudden surge of fluid coming out of this drill string on the surface, and that's called U-tube effect. So those 3 parameters will dictate if our cementation down the hole is successful or not, because we can't really see what's happening inside, so it's just some indicators. And sometimes we just can't find any indication of, at least, well, for YouTube, for example. So it indicates that when you don't have YouTube, it indicates that you don't actually have this column above these receptacles. So it means that your cements are actually losing into the hole. And so we kind of did some experimentation as well. So we perform cement drop job just after we do not really observe any YouTube effect. So we just drop some bunch of cement on the top of this receptacles. And this will be also the success criteria, or our observation about the cementing activities during this campaign. It involves like 21 wells in total. So it's only half of the wells drilled actually completed within the planned time frame. So you should prepare for some additional time every time you are using this technique. And 8 wells even exceeded the duration due to longer cement drilling intervals, additional squeeze cementing, longer waiting on cement periods, and also failure on cementing equipment. And it resulted in only 0.68 days per well. The average cementing time was 2.16 days per well without equipment failure, and 2.48 days per well with equipment failure. So this is the figure. And only 17 out of those 21 wells successfully achieved shear and bump plugs. 2 wells failed to achieve bump plug due to wiper and dart plug connection failure. So this is one of the phenomenon when because we run the liner at the same time while the wiper plug and also the dart is connected down the hole. So when you have relatively unslicked wells, it's gonna be you're gonna need some washing or work pipe on the well, and it could result to failure of shear pin. So you will not get any sign of shear pin. And the YouTube effect, it's even lower than what we expect. And the cement slurry, it gets higher, both for liner and also for tiebacks. And this is the conclusion. The success of tieback cementing operation depends on the success of liner cementing. And also the data indicates that the liner down with 300 GPM. Well, actually, this is the practice that we did at the site, and it deemed safe for the shear pin premature settings. To minimize pipe work, we have to ensure that the well is slick, just like what I said before. So I think that's all about this presentation. Thank you, Sigi. Thank you, everyone.
Thank you, Vicky. A few questions from the audience. Okay, I had one. I don't know. Are you using more cement with this method than traditional methods or other methods?
Definitely not, because we always encounter low zones, and with these methods, you actually only pump down like half of the volume of the height of the wells, of the depth of the well. So it's actually reducing the hydrostatic pressure at the bottom of the well. So it's in practical, it's less cement going into the formation. So,
questions from the audience? I have one quick question. You mentioned water behind the casing that will burp the casing when it heats up. Is that a big problem in Indonesia, or is it common?
Well, it depends on the it's different from one cases to another, but we don't actually evaluate that right after the well constructed. Well, we revisited the well again after like 2 at the soonest or 5 years for well intervention and check for the temperature and logging. And at that time, we also run some calipers. And like I would say that at least there are like 1 or 2 wells each of the sites encounter this problem with bulging casing due to pressure.
Thank you so much, Kiki.
Thank you.
Our next speaker, Steven Sachs, comes from Weltec. Weltec is a Danish company located in Denmark. Well, Stephen holds a degree in electronic engineering from Robert Gordon University in Aberdeen and recently returned to university to study geothermal and hydropower engineering. Stephen is Client Solution Manager at Welltec UK, where he serves as a member of the UK Welltec New Energy team. Stephen has more than 18 years of experience in robotic interventions, both office-based planning role and in the field. Welcome, Steve.
Thanks, Siggy. And yeah, the field time seems a long time ago these days. So, good afternoon. And as Siggy said, my name's Stephen Shanks. I'd like to talk a little bit about Welltec solutions for scale removal in geothermal wells. And I'm also going to go into some of the results we've had on some real-world testing we performed a couple of years ago. So, as you know, and as some of the previous speakers have gone into, scale build-up in geothermal wells is a known problem, gradually restricting output throughout the life of the well until remedial action is taken. So silica scale is found commonly here in Iceland and in higher temperature wells. And pipelines, of course, induced by flash vaporization is most commonly tackled by the use of inhibitors, as some people have mentioned already. When that's insufficient, heavy-duty interventions by coil tubing, a rig, or even a full workover, these are high-impact but high-cost methods of solving the issue. But another scale type commonly found in oil and gas, calcium carbonate, is where Welltec's scale milling technology cut its teeth. Along with barium sulfate, really hard stuff, back in the early 2000s, we began to see fantastic results removing even the hardest scales deposits using a lightweight wireline-based technology. The well miller. So this is Welltec's approach to this. This is an electro-hydraulic mechanical milling technique run on wireline. It can be deployed on standard 7/32 or 5/16 E-line cables, that's electric line, via lightweight crane rig up. We've designed our own proprietary milling bits to make the most of the torque and weight available to us to effectively, efficiently, but also aggressively remove scale from the wellbore. The tool, combined with Welltec's original innovation, the well tractor, delivers the weight on bit required, as well as providing reactive torque to prevent the whole BHA spinning. So the tractor is anchored into the tubing, or the liner, of course, and the miller removes the scale. And with this approach, there's no torque or load on the wireline itself. It's fully isolated. The Welltec well tractor, our original invention, so 30 years old now. And over those years, we've incrementally improved the performance of the tool and the design with no compromise on reliability. We perform thousands of operations with the well tractor every year and maintain service quality levels in excess of 99%. We're very proud of its reliability. The very latest generation is faster and more powerful, but advances in our power electronics mean the tool string uses much less power than its predecessors. And of course, less power means less heat generated. And this means we've been able to increase the rated temperatures we can run these services in over the whole Welltec fleet of tools. The very latest generation of tractors and millers is able to comfortably operate in well temperatures up to 185 degrees Celsius, which in this environment seems still like there might be work to be done, but it's ever increasing. We have a great track record with this. I'm sorry, Bruce, this is from oil and gas. But we have performed thousands of documented operations, and the records really begin in 2011, although Welltec has been operational since the early 90s. The 318 well tractor and miller have over 14,000 jobs under the belt. But the miller itself, certainly racking up many, many successful well interventions. And it's proven on calcium carbonate. And as I mentioned, our service quality, even with the miller involved, is extremely high. But I want to talk a little bit about reducing the impact, both to the cost of an operation, also to the physical footprint. A comparison of range of operations that we perform is shown here and highlights that simple wireline rig up via an on-site crane saves costs, operational time on-site, personnel numbers required, and as a result, reduces the HSE exposure. But the combined effect of these savings also results in a reduction in CO2 footprint, with an average Welltec operation saving between 7 and 8 tons of CO2 when compared to a similar coil tubing intervention. Apologies for the lack of reference on this, but we can show our working if required. So with all that said, can it be done in a geothermal well? So I want to talk a little bit about how we've tried to prove this technology. We configured a tool string as we would run it in a well, with the swivel device at the top of the tool with a head tension readout. The well tractor deliver that weight on bit and the reactive torque. As I said, it's anchored into the liner. And then the wheel miller below it. We also designed a 9.5-inch taper tungsten carbide mill bit. This was a bespoke mill bit featuring tungsten carbide teeth similar in appearance to a PDC drilling bit. This bit was chosen to be the most effective for removing scale from 9 5/8 casing or liners. This is the largest OD scale bit ever to be designed by a Weldtech, and as far as I'm aware, the largest milling bit to be run on wireline to date. So this is our testing. Thanks to our friends here in Iceland, we received a trial section of 9 5/8 casing fresh from a geothermal producer here. The casing had a significant buildup of silica scale and was typical of the type of condition we would like to remedy. Of course, the well conditions in northeast Scotland, this is performed in Aberdeen, were a little bit different from a TD and a flash steam producer, but it seemed the best place to start to verify our solution and capture our best practices. A few photos here of the mill bit and the casing before we began to mill. You can see there the tungsten carbide teeth. It's quite a unique design, as I say, bespoke design by Weldtech. We were aiming for a weight of bit of around 500 to 600 kilograms, entirely provided by the well tractor. This was pool tested at around 750 kilograms before the test, so able to maintain the 500 kilograms quite comfortably. We milled out a short 1.5 meter section, and it took around 50 minutes to complete. We monitored head tension the whole way along with the current consumption of the tool, which is the best indicator of the work being performed by it. What you can see here is how we see it, how our engineers would see this operation. So we have the current consumption of the tool here and the head tension. So this is the tension on the wireline. And what we're measuring here, and this is what we're looking for, is a steady decrease in current consumption with a corresponding increase in head tension. And that's indicating that the tool is working, clearing the scale, and then pulling on the tractor, ready to go forwards a little bit more. On completion of the mill, we could see that, that it had worked as intended and removed the scale almost to the full ID of the casing. You can see there are only minor deposits left. So looking to the future of this technology, well, what can be done? Well, tools with hydraulically expanding bit heads, as you can see here, are being developed in sizes and temperature ranges to suit geothermal applications. And even jetting tools, which can spot chemical treatments directly where they're needed, all run on the same platform. And to go back to the size of the operation, as you can see here, it's a lightweight crane-based rig up. And it can be used, it's urban environment friendly. So you've got low noise pollution, low light pollution, and limited POB required. 2 engineers plus a wireline crew is sufficient to run the operation. And another mention on the temperature, because I know that's a very common question when you're talking about robotic interventions in geothermal wells. From Q4 this year, all Weldtech's tools we rated for operation up to 185 degrees C for long duration. This is a non-flask design. They're designed to work for the life of the run rather than to a time limit. So in conclusion, yes, mechanically removing scale buildup in geothermal wells using nothing but an E-line rig up is not only feasible, but could be routine. And our testing shows very similar ROP and current load as we routinely see in oil and gas, milling calcium carbonate or barium sulfate. And we do this around the world. Wireline is faster, easier, and more cost-effective than mobilizing a rig or coiled tubing with vastly reduced environmental impact from noise, light, and CO2 footprint. We're always innovating to find the best efficient solution to downhole problems in all geothermal wells. So in conclusion, adopting Weldtech's technology for scale removal not only optimizes efficiency, but significantly reduces your environmental impact. So I invite you to consider these benefits for the next time that you have a geothermal producer with a restriction due to scale. Now, invite any questions at that point.
Thank you. Thank you, Stephen.
No problem.
Do we have questions for Stephen? One question here. NAS is running for us. Stephen had told me that his presentation was not that long, so we are not that much behind schedule.
Oh, did I get it sped up?
No, it's
I was happy to help.
So most of our cleanouts are done with the well flowing to carry
Sure.
the scale back out. So in the high temperature environments that were a lot of us working on, 185C is not hot enough. So
Sure.
what is causing the limit? What piece of the system is limiting your temperature? Is it the wire line? Or do you have elastomer seals? What's going on?
So, yeah, great question, and definitely very relevant for this. The limitation is electronics and the motor, basically, in the tool. So designing power electronics to deliver the kind of torque and force that we need to aggressively remove scale, the harder scales, which are a little bit harder to clear, just demands a lot on electronics generally. So you could make a very, very expensive electronic, which could run 250 degrees plus, but maybe only use it once. What we're looking for is repeatable reliability and incremental improvements. But it really is electronics. The tool itself is happy up to 200, maybe 250 degrees C. So once we improve the electronics a little bit more, then hopefully we can mill while flowing as well. But we also have a method of flowing downhole, which I'll maybe talk about another time, but happy to talk about it separately.
Other questions? I had a question, but you have already answered it because I'm asking for a friend. So if you have a live well and you cannot afford to shut it in or to kill it, do we have any methods for that? So you mentioned that briefly. What methods are you developing for that?
So there's no there's no limitation to flowing the well. If you can flow the well with a wire line in place, then that's fine, but the temperature then is the limit. We also have a tool which has the milling capability I showed there, but also with a turbine fitted downhole. So it circulates the fluids while we're there. That clears the cuttings, collects it in a baler, and then recovers that to surface. That could also be applicable in geothermal wells, of course. It has limited capacity, so it adds to the number of runs that you'd have to complete. But then you'd be able to leave the well static in that situation.
Thank you, Stephen.
Thank you.
Our last speaker is Erik Neumann. Erik studied mechanical engineering, Master of Science at Technical University in Dresden, Germany. He is now working the chair of construction machinery at TU in Dresden as a research associate. Parallel to his work, he is a PhD student working with the topic reliability enhancement of electropulse power tools. Your floor is yours.
Great. So I've got the pleasure to close the loop of this session and proceed with Rochelle's topic, kind of. These are similar tools, although kind of completely different. So I'll try to present you a novel deep drilling technology that is currently covered within the scope of an ongoing research project, and then talk a bit about scale removal with electropulse power technology. I'll make it a little shorter and just say EPP technology. Right, so this project for the deep drilling is called Deep Light. It is funded by Geothermica. They supplied us with 3 million euros over a time span of 3 years, but we have to share it between our 12 partner organizations. You can see them here on the right-hand side. There are 5 research organizations from the US, Netherlands, and Germany involved. We've got some technology providing companies and partners from Iceland, Turkey, and the Netherlands who are into geothermal exploration, drilling experts, or operators of geothermal power plants who direct our research to the right direction. What are our motivations behind this project? We learned from Bruce that drilling is not too expensive. Maybe we are just too poor. Therefore, we want to lower the drilling cost. When developing a novel technology, also its environmental friendliness is a really important topic. We aim to increase the well productivity by heading for larger well diameters. And last but not least, this geothermal well is only sustainable if it has a long lifetime and is stable over this lifetime. On the right-hand side, you can see our approaches how to achieve the mentioned targets. And as corporate, the EPP bit can be seen. So this is not anymore a mechanical drill bit. It drills with high voltage pulses. And that means there is no cutting force needed in order to create cuttings and crush rock. That allows to work with way smaller rigs. Furthermore, no mechanical drilling means no mechanical wear. So that saves you time and money for round trips that is conventionally needed to exchange the bit. This EPP bit also allows to work with a casing while drilling procedure. That's again faster and cheaper. And I think you all know when setting up such a new system, you also have to touch the mod system. So the mod is adapted to meet the needs of drilling technology and the EPP bit. There are our colleagues from the US and Iceland busy with developing a smart cement sealing system, and ISOR is helping out with their flexible couplings to achieve this long lifetime of the production well. Last but not least, all these subtopics need to be seen as one system, so we're putting a lot of effort into the system integration. How does now the electropulse power technology work? We're always having two electrodes, high voltage electrode and grounded electrode, that are placed on a solid dielectric material, which is in our case rock. This setup is then surrounded by a liquid dielectric insulating medium, which can be, in the ideal case, oil or diesel, but water, tap water, deionized water, or water-based mud work as well. If now an high voltage pulse is applied to one electrode, an electric field is built up between both electrodes inside the liquid medium and inside the rock. If now the impulse is high and steep enough, something weird happens. The rock becomes an insulator, whereas the rock becomes a conductor, whereas the liquid is an insulator. And that allows an electric discharge through the solid material, and a plasma channel between both electrodes is occurring. There is a discharge current flowing through this plasma channel. The channel is heated up, expands, and the rock is blasted from the inside. So we're working against the tensile strength of the rock, which is much lower than the compressive strength. That way cuttings are produced. That's all the science behind it, and the rest is just engineering. At Dresden, a prototype of such an EPP drill bit was developed, and it contains 3 parts. That's the power train, the pulse voltage generator, the electrodes, and all is accommodated in a housing. So what the powertrain does, it converts the hydraulic energy coming from the mod into a 40 kilovolt DC charging voltage. This charging voltage is then fed into the pulse voltage generator. The name already says it's delivering voltage pulses towards the electrodes, which are exactly these electrodes and equivalent to mechanical cutters. Physically, now the bottom section of this bit has been built, so the pulse voltage generator, housing and electrodes. Component tests have been carried out, as well as a system test. And here you can see the result of this system test. There was a hole drilled in granite, here still under water-based mud, but this was a great success and proof that not only the fundamental concept works, but it's also possible to build a bit out of it which fits into such a small borehole. Small is always relative, because in high voltage industry, huge components are very common. Simply for insulating purposes, we do not have that much space in a borehole. Here you can see the current prototype of this EPP bit in our little scientific test rig. There are two stages of the pulse voltage generator consisting of coils, capacitors, and spark gaps. What we have so far is this 12.25-inch hole that was drilled in granite. The pulse parameters are 600,000 volts, so that's a huge number, which we can build up within 100 nanoseconds. And that allows us to reach an equivalent mechanical specific energy of only 200 joules per cubic centimeter. So this is this efficiency and this benefit of the EPP technology. From calculations, we know that we could reach a rate of penetration of about a meter per hour in granite here still under water-based mod. And two more advantages. No rotation of this bit is required in order to drill a hole, because again, no mechanical force and no cutting force is needed. That means also no weight on bit is needed, and that simplifies some issues. What we're currently about to work on, we're elevating the power level from 15 to 40 kilowatts, simply to increase ROP. We are about to get this prototype out of the laboratory onto a real rig. You'll see a picture of this in a minute. And we're doing the shift from oil-based mod towards water-based mod. If you're now wondering, what does that mean? So this is my daily work. There are lifetime tests of capacitors performed. We are having a look, how do they behave under various power levels. We are doing electric simulations, so converting this prototype into an electric network in order to simulate the voltage shape, or the shape of the voltage pulse. So here, for example, the difference, the green curve is under oil-based mod, whereas the same system, nothing changed, just under water-based mod, shows a rapid drop in amplitude of this voltage pulse. Also, ordinary CAD FEM simulations are carried out as we are using many plastic parts for insulating purposes, sealing, and mechanical fixture purposes. That's about the theory. The practical work involves functional tests. So currently we're right here. We've got the component and system validation. The next step would be to test this prototype under various flushing media, different additives of the flushing, how it behaves with different kinds of rock. So sandstone, limestone is not a problem. Granite also works. Yeah, others would be also interesting to test. Then we have to prove that this prototype works under pressure. Why that? Electric discharge mechanisms change drastically when you exceed a certain pressure threshold. And eventually, we're shipping the prototype to the Netherlands to our partners at TNO and test the bit there at their scientific test rig. Now you knew everything about drilling with electropulse power technology, and you could wonder, is it also possible to drill scales out of a casing? And of course, yes it is, big surprise. Here you can see our load and parameters that we consumed, that we assumed. We were shrinking down the casing diameter from 12.25 to 4.5 inch. Assumed a scale thickness of 1 to 10 millimeters. The kind of scale does not really have a big impact here. As long as it's hard and brittle, it's fine. Machine was constructed and built according to these boundary conditions. It's a pretty small and light machine. The prototype can be seen here at the right. So there are again two stages of the pulse voltage generator with the sealing part of the housing underneath and the prototype of the electrodes. And the idea is now to have just one electrode, which is the high voltage electrode, the red part. Then you've got the scales right and left, and the casing itself as a grounded electrode here, and a high voltage discharge, which is going through the scales, goes directly into the casing and removes the scales. We proved this with an artificial concrete scale, and it works perfectly. So I hope that I could show you that some fundamental research was already carried out. We also developed lots of components and did the system integration, reached technology readiness levels up to 6. And this is where usually industry comes in, takes over this topic and develops it to a ready product. Thanks, that's it from my side.
Thank you, Eric. Questions from the audience? One question here. This method looks, I see a Star Wars movie, a beam drilling down a well.
Hi, Diana Tranco. The question you mentioned, you get your energy, the electric energy from the fluids?
Yes, regarding the drill bit, there is the idea to have a turbine that converts hydraulic energy to mechanical energy. Then there is a gearbox simply to increase the RPMs. Then you've got an electric generator which outputs a AC voltage of about 800 volts. Then there is a transformer which brings it to 40 kilovolts, and then you've got a rectifier which outputs a DC 40 kilovolt voltage.
What were the specifications of the pumps for the test on the granite for obtaining 1 meter per hour?
Of the pumps, the mud pumps? No.
Yes, for the fluid?
No, this section of the powertrain has been constructed and calculated, but never been tested. So the single components exist and they fit to each other, but it has not been tested as a subsystem.
Any other questions?
How difficult would it be to drive into the deep? I mean, to do directional or establish the direction of the well. Direction drilling.
I know that there are thoughts about this topic. I think not that difficult. The prototype that I showed you is 9 meters long. It cuts away a little more than 12.25 inch, so there is some room to steer this bit. How to steer it exactly, sorry, that's none of my business, but there are ideas to create kind of a worm going through Earth and steer like that.
Thank you, Eric. Thank you. Now we have come to the end of the session. This has been very interesting and I have learned a lot, and I guess that you have done too. I would like to thank the speakers for the presentation and for you all to attend these sessions. Now we will have a coffee break and then we will all attend the closing plenary that starts at 3 o'clock. Thank you all. Thank you so much.